All right, number 5, let f be a twice differentiable function. So this means it's going to be continuous on the interval a to b, which the following is sufficient to conclude that f is an absolute maximum at x equals c. So we're looking for absolute maximum. So number 1 says the derivative at c is 0. So we know that means there's at c. So we got a and b. At c, the horizontal tangent line is 0, and the derivative is negative, so this is concave down here. So this we know is a relative maximum, but we don't know what else happens here. It doesn't tell us a whole lot. So the graph could look like this, or it could look like this, and that's just a relative maximum, not necessarily the absolute maximum. So that is not enough information. Number 2 says C is the only critical point in A, B. So that's really helpful. If that was in number 1, that would have helped us out. Maybe not. So number 2, C is the only critical point. So we still have C, we have A, we have B. It's the only critical point, and we know that the first derivative is positive, which means f is increasing when x is less than c. So it's increasing. And then we know it's decreasing. This is negative, so it's decreasing. I should say f is decreasing for x is greater than c. And since this is the only critical point, there's no changes of direction, so this graph can't come back up and get larger. And so this is sufficient. And number 3, C is the only critical point, so that's the same idea. So the only critical point in A, B, and f of C is greater than f of A, and f of C is greater than f of B. So that means C is higher than A, and C is higher than B, and so since it's the only critical point, this has to be the maximum. It's kind of like the candidates test. If we were to put our critical point and then our 2 endpoints, it's saying C. When you put C in, it will give you the highest value or greatest, and so that is the absolute maximum because the extreme value theorem says there has to be a maximum, and so we are able to find it using the candidates test. So this is correct, so both 2 and 3. So choice D. Moving on to number 6. Let f be a twice differentiable function. Selected values of the first and second derivative are shown. Which statements are true? All right. Well, let's take a look over here at this table. We have the first derivative being 0 at 1, 2, and 3. So those are critical numbers. Now at 2, so we could, if we want to, we could say here's 1, 2, and 3 critical numbers. And so we know it's concave down because this is negative. So since the second derivative is negative, it's concave down there. And so that has to be a maximum. So f has a relative maximum at 1. Okay, so that has to be true. Inflection point. Well, first derivative is 0, second derivative is 0. So it could be an inflection point. However, it doesn't have to be because this could come down here. It could be really flat here, kind of like an x to the fourth, the vertex of an x to the fourth, and then go back up. So this could have been first derivative is 0 and the second derivative is 0. So that would still be concave up. So that doesn't tell us anything. Again, also, all these things could happen between here. So this isn't necessarily true. It could be true, but not necessarily true. And relative minimum at x equals 3, let's check that out. Derivative is 0, so it's a critical number. So critical number, and this is positive, and so this is concave up. So concave up, which means this has to be a relative minimum. And so this one is true. So it looks like this will be 1 and 3 only. All right, moving on to number 7. Function f is increasing on the interval 0 to 6 and has exactly 2 points of inflection. Which of the following could be the graph of f prime of x? All right, so it's increasing from 0 to 6. So increasing. So going up left to right, we don't know, well, we know a few things. It has 2 points of inflection on the interval. So it changes from concave up to concave down, and then concave down to concave up, or vice versa. Which of the following could be the graph? So a graph that's always above the x-axis. So which of the following could be the graph of f, the derivative of f? So we know that it's increasing. So increasing tells us the first derivative is positive. And so that means the first derivative is above the x-axis. All right, so in this case, it has to be above the x-axis. So this is out. We know it's the graph. Okay, so that one's out. Has exactly 2 points of inflection. So 2 points of inflection means that if we think of this graph, and let's just draw 2 points of inflection. So here's one, and here's one. This is our graph is increasing, but then it's starting not to increase as much. And so that's going to be a local extrema when these change direction. Changing from concave up to concave down says that the slope, well, so it's going to be 2 extrema. So this, it's always above the x-axis, and it has 2 local extremas, so it has to be this. And this isn't one of the ones like above where you had 3 choices and then had to pick which one's which. So a graph is always above the x-axis with 2 local extrema.